So, hello everyone, and welcome to our We Meet at Digital Days. My name is Eleni Stark, and I will moderate this presentation today. We are very pleased that you took the time to participate in our virtual conference. The topic of today's presentation is High Frequency Common Mode, Noise and Solutions. Our speaker is Muhammad Ali Khalid. He will hold the presentation and also will answer your questions. Before we start with the presentation itself, I would like to point out one thing. You are muted during the presentation. This means that you cannot ask us questions via microphone during the presentation. Nevertheless, you have the opportunity to ask us all your questions during the presentation via the chat function. You'll find the chat function in the control panel. The presentation will be about 30 minutes long. The chat questions will then be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all your questions promptly. At the end of the presentation, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will receive the link to the presentation in the next few days. The recording will be available at our website shortly. Now I will hand over to our speaker, Ali, and I wish you an exciting presentation.
Hello, everyone, and welcome from my side. My name is Muhammad Ali Khalid, and I'm the product manager for EMC and inductive solutions. Today, we will be talking about high frequency common mode noise in extremely high speed digital circuits. So here is the agenda of today's webinar. We will start off with the digital interfaces and the differential signaling. Then we will talk about some noise issues and what are the existing solutions. And then we will introduce a totally new technology, specially designed for the 2.45 gigahertz common mode noise. And in the end, we will take a brief look at the applications which are related to this technology. So just getting into the presentation. Here you can see the switching speeds of some of the modern digital circuits. As you can see that these speeds are getting higher and higher as we are going through time. And with the high switching speeds, we are now able to achieve very high data rates and bandwidth. These are some of the individual data line switching speeds for the state-of-the-art communication interfaces. And here you can also see the USB 4 specification. It was released a couple of years ago, and it is actually already available for some of the applications. And if we look closely at the speeds, we can see the general trend is towards the increased frequency of switching or the increased data rates. Here are some of the maximum data rates for the standards with all the data lines active. This means that that it includes all the data lines available in the particular standard. You can see that we have come a long way from the USB 2, and now we are reaching the data speeds of 40 gigabit per second with USB 4. So just a brief overview about differential signaling. So in the slide, you can see that there is a transmission line. So what is a transmission line? The transmission line is a specialized conductor which is used for the differential transmission of high frequency data, like for example in USB or in HDMI. As the frequency gets higher, the parasitic effects of the signal transfer become more and more pronounced. and this affects the impedance and the power transfer. Thus, the conducting media has to be appropriately designed. So in the slide, you can see a microstrip line, which is one of the most common examples of a transmission line. And it basically consists of 3 layers. We can see that conducting strip on the top, a dielectric with a specific permittivity, and then a ground plane on the bottom. The layout can be easily designed by various available RF microwave simulation softwares, and some of them are also free to use online. You can also visit, you can just Google it, microstrip line calculators in Google, and you can have some of the free to use online tools at your disposal. So the differential signaling is used for the transmission of data in these high-speed interfaces. And the differential transmission method uses basically 2 lines or conductors which are side by side with the same amplitude current flowing in opposite directions. But why do we even use differential signaling for the data transmission? Why not just use one line or conductor? This is because of the advantages that come with the differential signaling of that data. And some of these advantages are mentioned here in the slide. So the first one is the reduced EMI in both incoming and outgoing direction. So any incoming electromagnetic interference or crosstalk from other noisy traces gets distributed evenly between the positive and negative lines or traces, and which means that the noise is already reduced, or the change in amplitude to the is already reduced. The second point is about the differential signals. They also generate their own EMI while transmitting information. So, however, because the positive and negative signals in a differential circuit share the same polarity and distance, this effectively cancels out any EMI emissions. So for the second point, for the low voltages. So the differential signals also have the added benefit of being able to operate at lower voltages compared to the single-ended signals. So, and with lower voltages, we get the benefit of being able to use lower reduced power and reduced EMI emissions. And the third point is about high data rates. The decreased voltage amplitude leads to short rise and fall times for the switching circuits, which means faster switching and hence increased data rates. So where does the common mode noise come in all of this scenario? So the common mode noise is the type of noise that is conducted on both lines in the same direction. In ideal case, the differential lines should be able to cancel the common mode noise, and the output or the noise should be rejected. But this seldom happens. In reality, there's always minute differences on the lines. For example, these differences could be voltage or the impedance difference on the two conductors. Or there can be a small delay in the switching times on both lines. So these small mismatches get more pronounced with increasingly high clock frequencies. Thus, the signals used in the modern data and telecommunications are a serious potential source of RF interference. And these signals can also influence other devices and systems nearby. Now, we will discuss some of the basic techniques to keep the EMI level to minimum when designing the parallel differential lines. So this slide is associated with the design part of the EMI. So for example, we can keep the signal amplitude to the minimum. It means that less EMI as less time is required for changing the signal state. Or the length of the two traces in differential pairs should be kept equal. This becomes especially important with higher rise and fall times of the signal. The physical isolation is probably the most obvious technique since we do not live in an ideal world, so isolation is never perfect. And but at the gigahertz frequencies, the practical isolation values can be between 20 to 40 dB. And the impedance variation should be kept to minimum, which means paying special attention to the width of the traces, coupling, and the dielectric material and the stack up of the PCB. So even with the noise mitigation techniques that we just discussed, it is unavoidable to have noise-free communication at these high frequencies. And so we look for the further techniques or solutions to remove the common mode noise from the system. And by appropriate protective circuitry, it is possible to suppress the interference and at the same time let the transmitted signal pass unaffected. Shielding, the first one, is perhaps the most commonly known solution against the radiated noise. And for lower frequencies, this is actually, it works quite good, but at millimeter wave frequencies, the opening in the shielding can be a potential source of RF interference itself. And filters and chokes are very effective means of protecting the data lines. They can substantially enhance the characteristic symmetry of the transmission line and thus contribute further to the increasing interference immunity and at the same time reducing the emitted interference. Here is a brief comparison between these solutions that we just discussed. So you can see that the shielding is highly dependent on the mechanical design, and due to openings in the shielding design, the RF noise suppression is compromised at higher frequencies. When we talk about the conventional ferrite-based common mode chokes or filters, they are very effective, no doubt, against the broadband RF noise. But as we move towards the higher gigahertz or millimeter wave frequencies, we see the limitations of the ferrite in coping with the signal integrity, and while at the same time also providing the required suppression for the common mode noise. Compared to the other possible solutions, the ceramic-based choke not only provides much better noise suppression, but also stable performance for the useful data signal. Here I will talk about our innovative common mode choke, which is WECCMF, ceramic common mode filter. It is basically a sensitivity improvement solution for your wireless devices at 2.4 gigahertz. This means that potentially the common mode choke or filter can be used in any wireless communication device which also has a high-speed digital switching interface. The common examples include smartphones or tablets, notebooks, routers, IoT-enabled devices, etc. The multi-layer design is made up of low temperature co-fired ceramic material, which is also known as LTCC material. And the advantages of that material is that it is very resilient and has low losses in higher gigahertz frequency bands. The differential mode transmission and common mode suppression are controlled by the transmission lines in the form of metallization inside the LTCC material. Here we see the difference between this filter and the conventional ferrite-based common mode chokes. And the main difference comes in the form of high common mode suppression and a very high frequency range or limitation for the differential data line signal. So just to give a brief example of where this filter can be used is that here's an example of a 2.4 gigahertz noise generated by USB 3.1 generation 1 transmitted signal. So the source for this data is Intel's white paper, which is also titled USB 3 Impact on 2.4 gigahertz wireless devices. So as you can see, if you take a look at the sync function in the slide, the USB 3 specification requires the data to be scrambled and uses spread spectrum technique on the clock. And this can be also modeled as a sync function that we see. The sync or the sampling function is the frequency domain representation for the spectrum analysis, which is obtained by the Fourier transform of the rectangular signal. But we do not need to get in depth into this topic of the Fourier transform or what is a sync function. What is important to note here is that the data spectrum for USB 3 signal is very broadband, ranging from DC to about 5 gigahertz. We can totally ignore the side lobes. In fact, the design is based on ensuring that the side lobes are neglected. So here is the data spectrum of the USB 3 transmit pair signals from a laptop notebook measured by directly probing in and comparing it to the typical Wi-Fi received signal strength. So here you can see if a wireless device is working at this frequency band and is placed close to a USB 3 radiation channel, it can pick up the broadband noise and reduce the signal to noise ratio, which can result in antenna descents. We will talk about antenna descents in the coming slides. But important here is to note that depending on the distance and the receiver sensitivity, the noise generated by USB 3 has the ability to potentially interfere with the wireless communication, which could be a Wi-Fi signal or a Bluetooth signal or a 4G signal. Here is another graphic or a diagram which basically elaborates this. The 2.4 gigahertz ISM band is perhaps the most extensively used band for unlicensed wireless devices. And what we see here is that the switching speed for the USB 3 is 5 gigabit per second. We're talking about generation 1. This means that the USB circuit is handling data on a very broad spectrum and at the same time radiating noise from DC to 5 gigahertz. And this spectrum also includes our frequency of interest, which is 2.45 gigahertz for our Wi-Fi antenna. And if this Wi-Fi antenna or wireless device, which is operating nearby, is at this frequency, it can pick up the noise and result in communication failure. Here is a small background for signal to noise ratio before we can jump into antenna descents. So it is important to talk about this SNR or signal to noise ratio because it is the reason why we see problems in communication due to introduction of noise. The higher noise leads to lower SNR levels, which can result in antenna descents. And what is signal to noise ratio? It is basically the difference, or it indicates the difference of an interference signal related to the useful signal of the circuit. So important here is to note that typically a higher SNR results in fewer errors and higher throughput, and which is more desirable. And thus we come to the antenna descents. So descents is the degradation in sensitivity due to noise sources. So here's a very simple graph which explains this. Generally speaking, the noise floor should be much below the level of the useful signal. But if the noise level increases due to poor SNR, it can make it very difficult for the antenna at the receiver to pick up the useful signal. This phenomena is called antenna descent, and it is one of the main reasons why we have the communication failures at 2.4 gigahertz. So after all this background from the SNR and antenna descents, we can see the electrical parameters for our new innovative WEC-CMF common mode filter. And here you can see the typical S parameters for the common mode filter, which includes insertion loss and the differential mode insertion loss and common mode suppression. You can see that the differential mode is almost a straight line up to 10 gigahertz or even more, and it is well within 3 dB limits. And the common mode suppression is more than 40 dB in some cases at the Wi-Fi and Bluetooth frequencies. Here is the inner structure or the block diagram of the filter, which explains the working principle. The filter is basically a combination of low pass and a band stop filter, or we can say notch filter. The patented internal structure is quite complex, and it comprises of layers of metallization. So we will not go too deep into that. So, but what's important here is that the differential structure is electromagnetically coupled to the reference potential, and the reference potential structure, the ground structure, and the ground layer are electrically connected to each other. And here is the equivalent circuit for the common mode noise suppression circuit. Consists of 5 stages, or we can like fifth order filter. So higher order filters provide greater roll-off rates, as we all know, between the pass band and the stop band. And the roll-off is basically the steepness of the filter transfer function with frequency. And as the stages of the filter are increased, the stop band attenuation gets better and better. Here is an example of the CCMF in real life Wi-Fi throughput test. The 3 different cases of channel loss are shown in this diagram or in this graph, and we can see the improvements due to the WEC-CMF deployment. The higher the channel loss, lower the Wi-Fi performance, but thanks to our filter, we have been able to reduce the common mode noise and antenna descents to get the acceptable Wi-Fi performance. On this slide, we have some of the applications where we can use our high-speed filter and successfully remove the noise. You can see almost all of the commonly used I/O standards here, including USB, HDMI, Thunderbolt, SATA, etc. So here we will again talk a little bit about the applications. So any device, with whether it is a smartphone, tablet, router, laptop, or gaming console, or any IoT device, is a potential application for this filter. And especially with the advent of 5G and the gigahertz bands getting more congested, it is safe to say that in the future we will see more and more of common mode noise at higher frequencies. So, but there is no need to worry about that, because here at Würth Elektronik, we, as your EMC specialist, is already working on the design and addition of next generation chokes to our extensive portfolio. In the meantime, we can help you also with your noise problems in any given frequency range. And we have our extensive list of common mode chokes, but just to focus on the high frequency common mode noise, here you can see that the common mode noise filter, the ceramic based filter, starts working from about USB 3 standard, which means 5 gigabit per second switching technology, and it keeps on going until Thunderbolt 3 or USB 4 standard. So thank you everyone for listening to the presentation. You can go ahead and ask any questions that you have in mind.
So, Ali, thank you very much for this interesting presentation. Like you already said, now we would like to turn our attention to the questions of our participants, and we will just wait a little until some questions have come in. I've already seen 2 questions, but maybe we will have a few more. Yeah. In the meantime, we can start with the first question already. The first question is, why only 2.4 gigahertz noise suppression for ceramic choke?
Yep, this is a very good question. So, because as I already explained, that with the high speeds of the switching standards, the common mode noise is being generated at higher and higher frequency. And the most important frequency point in this high frequency region is wireless communication point, which is Wi-Fi or Bluetooth, which happens at 2.4 gigahertz. That is the reason we focus this frequency point, and this choke has been designed specifically to counter this issue at Wi-Fi frequencies. But it's not just 2.4 gigahertz, as you could see in the S parameter slide, that we also have a dual mode choke which works at both 2.4 gigahertz and 5.5 gigahertz, around 5 to 6 gigahertz roughly, to cater for both the Wi-Fi bands, basically.
Thank you very much. The second question that we have, can you also please explain antenna descents again?
So yes, the antenna descents is basically the desensitization of the antenna due to lots of noise present at the same frequency. Just to give an example, a Wi-Fi antenna which works at 2.45 gigahertz, and if there is a lot of noise also present at 2.4 gigahertz due to these high-speed standards, then the Wi-Fi antenna at your home is not able to see the useful signal for the communication, and that's why there will be a communication failure, and this phenomena is known as antenna descents.
Thank you very much for this explanation. We have a few more questions. One question is a bit more complicated and very long, so we would just skip that one and answer the person directly via email. So no worries, we will answer all the questions that have come in. So just let me check the next questions that we have. So yeah, one question, how to connect the ground pin from CCMF ideally, especially if you use differential microstrip lines.
So basically for this, we have a whole guideline on our website. If you visit WECCMF page on the Würth Elektronik website, you will be able to see all the recommendations for the layout for different circuits, like for example USB or HDMI or DisplayPort, etc. And normally CCMF is a 6-port common mode choke, which is not so common to see. So, and the 2 ports in the center are reserved for the ground connection. But for the specific question related to how to route it on your circuit, you can visit the whole guideline on the website.
Thank you very much. So the next question, is it possible to use these filters in combination, either series or parallel, to achieve better filtering?
It's not recommended to use them in combination because a filter is still an extra device on your data line, which also affects the data line signal. And with the one filter, we can ensure that the amount of losses are within the limits of what we are showing in the data sheet. So that's why it's always recommended to use just one filter on the one data line and to be sure that your data signal remains untouched or it's as intended.
Okay, thank you very much. So I see 2 more questions. Just let me check them. If I filter the differential signal with the CCMF, would USB 3.2, for example, work properly, or will I have a problem with the USB signal because I filter some frequencies?
It depends. So this is also a good question. So because as you know, that USB 3.2 has a lot of variations. So a USB 3.2 could mean 5 gigabit per second line. It could also mean 10 gigabit per second line, or it could mean 20 gigabit per second line, depending on which generation it is. It's generation 1, generation 2, generation 2x2, generation 2x1. It's a the people who are working with USB standards know all these differences, but just to be sure, you just have to check what is the maximum data line speed on this specific USB 3.2 generation. Is it 5 gigabit per second? Is it 10 gigabit per second? So, and then you can compare it with the limitation for our this ceramic filters. So we also have different variations of filters depending on the inner construction. So some of the filters have the cutoff frequency till 8 gigahertz, some of them had 10 gigahertz, and some have more than 12 gigahertz. So depending on the line, so it has to be chosen depending on the uh, data rate or the switching speed of that USB 3.2 standard.
Thank you very much, Ali. So we have one more question, which is also a bit more complicated to answer in this webinar, but we will come back to the person who asked. So don't worry. As I mentioned before, you will always get an answer to your question. For now, I don't see any questions left. So in this case, I will just thank you once again, Ali, for this interesting presentation. I hope everyone, like I did, enjoyed. And yeah, thanks here. I just want to draw your attention to our next presentation, which will start at 4 p.m., which is about yeah, why, what, how, a beginner's guide to crystals and oscillators. It will start at 4 p.m. and this will be our last presentation for today. I hope you will come to that one also. And yes, I just want to thank you all for your attention and see you later for the next presentation.
Thank
Bye-bye.
you. Bye.